In this presentation, we will discuss different types of relations. So let's get started. First, we will discuss reflexive relation. A relation R on a set A is called reflexive if A comma A belong to R for every element A belong to A. Now this is quite interesting. We are talking about relation R on a set A. Okay. A relation R on a set A is called reflexive if A comma A, this particular ordered pair, okay, I'm talking about this form where first element is equal to second element in an ordered pair, okay. If A comma A belong to R for every element A belong to set A. In other words, for all A comma A must belong to R. As simple as that, okay. Let's discuss one example. Let's say A is a set which consists of these elements and we have an R1 relation which consists of these ordered pairs. We have 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 4, 4. These are all the ordered pairs inside R1 relation. Relation R1 is reflexive because it contains all ordered pairs of the form A comma A for every element A belong to A. For every element A belong to A. Okay. That means for every element inside set A, 1, 2, 3, 4, we have an ordered pair of the form A comma A. That is, we have all the ordered pairs 1, 1, 2, 2, 3, 3, 4, 4 inside relation R1. You can see that 1, 1 is there, 2, 2 is there, 3, 3 is there, 4, 4 is also there, right? Therefore, it is clear that R1 is reflexive. Let's see one more relation. Let's say R2 is a relation which consists of these ordered pairs 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, 4, 4. This relation is not reflexive, let me tell you, because the ordered pair 3, 3 is not in R2. We have 1, 1, we have 2, 2, we have 4, 4, but there is no 3, 3 inside R2. Hence, R2 is not reflexive, okay? Now let's discuss the second type, that is irreflexive relation. A relation R on a set A is called irreflexive if for all A belong to A comma A does not belong to R. This is just opposite of what we have seen in reflexive relation. I am talking about relation R on a set A. This relation is called irreflexive if for all A belong to A. For every element A belong to A comma A must not belong to relation R. Let's consider one example. Let's say we have this set A which is similar to the set we have taken in reflexive relation. Now we are considering this R3 relation where we have all these ordered pairs 1, 2, 2, 1, 3, 3, 4, 4. Now this relation is not irreflexive, let me tell you, because 3, 3 and 4, 4 is there in R3. We are talking about every element A that belong to A, right? This ordered pair, that is A comma A, must not belong to R. But as you can see, 3, 3 and 4, 4 is there in R3. And let me tell you, this R4 relation is irreflexive. Here we have these two ordered pairs 1, 2, 2, 1. But there is no ordered pair of the form A comma A inside this relation R4. Therefore, this relation is irreflexive. Now let's discuss the third type of relation, that is symmetric relation. A relation R on a set A is called symmetric if B comma A belong to R holds when A comma B belong to R for all A comma B belong to A. Now here, if A comma B belong to R is true, then B comma A belong to R must be true, okay? This is called symmetric. Then the relation R is called symmetric relation. In other words, relation R on a set A is symmetric if for all A for all B, A comma B belong to R implies B comma A belong to R, right? This is an implication. If A comma B belong to R is true, then B comma A belong to R must be true. Let's consider one example. Let's say we have a relation R5 on set A, similar set, that is 1, 2, 3, 4. This relation is defined on this set A. Let's say in this relation we have these ordered pairs 1, 1, 1, 2, 2, 1, 2, 2. Now this relation is symmetric, let me tell you, because for 1, 2 we have 2, 1, right? And there is no need to check this 1, 1 and 2, 2. Obviously, this relation R5 is symmetric. Because for every A comma B belong to R5, B comma A does belong to R5. Here we have 1, 2, then 2, 1 must be there in R5 and you can see that 2, 1 is there in R5, right? There is no need to check for 1, 1 and 2, 2, let me tell you, okay? And let's consider one more relation. Here we have relation R6 which consists of these ordered pairs 1, 1, 1, 2, 1, 3, 1, 4. You can see that for 1, 2 we do not have 2, 1. So from this point itself we can say this relation is not symmetric. Right? Same is true for 1, 3 and 1, 4 as well. For 1, 3, we do not have 3, 1 inside R6. For 1, 4, we do not have 4, 1 inside R6. So it is clear that relation R6 is not symmetric at all. Now let's discuss the fourth type of relation, that is antisymmetric relation. A relation R on a set A is called antisymmetric if for all A for all B, A comma B belong to R and B comma A belong to R implies A is equal to B. Whenever we have a comma b in R, we will never have b comma a in R until or unless a is equal to b. As simple as that. If let's say a comma b belong to R and b comma a also belong to R, then according to an antisymmetric relation, a must be equal to b. Then we can say relation R is antisymmetric. Okay. For example, let's say we have this relation R7 which consists of these ordered pairs 1, 1, 2, 1. Now let me tell you this relation is antisymmetric because 2, 1 is in R7 but 1, 2 is not in R7. You can see that 2, 1 is there in R7 but 1, 2 is not there in R7. Therefore, this relation is antisymmetric. Here we must note this down. Here 1, 1 is allowed because it has been said that if a comma b belong to R and b comma a belong to R, then a must be equal to b. You can see that a is equal to b, right? But here we have 2, 1. If we have 1, 2 in R7, then obviously this relation is not antisymmetric because here if for 2, 1 we have 1, 2 in R7, then this relation is not antisymmetric. Currently we only have 2, 1 in relation R7, therefore relation R7 is antisymmetric. Okay friends, this is it for now. I will discuss the rest of the types in the next lecture.